Welcome PCS members and friends to our today's PCS IBS seminar. It is a great pleasure to have with us today Alexander Gresch from Heinrich Heine University in Düsseldorf, excuse me. And I would like to invite our scientific host, Dario, to introduce our speaker. Please, Dario.
Okay, thank you, Thielen. It's a pleasure to have here Alexander today. It's also a pleasure that the name of the university has been said by Thielen, such that I don't have to worry about that. So, so let me introduce our speaker. So Alexander is a PhD student in Düsseldorf. He's very young, but he has already a quite large amount of publications, including a PRL in 2018. And his PhD studies are mostly related to quantum computing, quantum algorithms, deep learning, and so on. So very, let's say, fancy and modern topics. And recently he wrote, together with his collaborators, a paper about a scalable approach to many-body localization, which is a topic that here in IBS or at least I like a lot. So that is the reason why I was really happy to have him here to talk about the scalable approach to many-body localization via quantum data. And Alexander, now is your moment. You can speak. Thanks.
Thanks a lot for the kind introduction. Hello from my side. Good morning from my side. Good evening to you. Thanks a lot for the invitation and the kind words. Yes, as already said, I would like to give some talk about the recent preprint of ours using the scalable approach to MBL via quantum data. This is joint work together with Lennart Bittel under the supervision of junior Professor Martin Kliesch here at Düsseldorf. So Heinrich Heine was well pronounced. Thanks a lot. Yes, our motivation of our talk we summarize in like the following question, and it reads as whether quantum data, and I'll define what it means for us in a minute, allows for practical solutions to otherwise difficult computational problems. Maybe let's dissect this sentence a bit. So with quantum data, we refer to everything which comes from really a quantum experiment, or at least a numerical simulation thereof. And for example, so this could be like you pick your favorite quantum experiment, and it delivers us some data, but you can also picture it using a quantum simulation of a quantum experiment. For example, if your quantum experiment you would like to perform has some restrictions on some platform and you would like to simulate it using another platform. This might also be applicable here. And we take this data now as a given. So it has to come somewhere from somewhere. And this is also not really not a trivial task at all, of course. But we ask the question, once we have it, can we do something more instead of not having it, so to say? And this should be practical solutions, meaning that we would like to do something efficiently in the number of the system size we're considering, of the quantum experiment size or so, as well as the data we are given. So this will hint to something like machine learning, of course, already. And the difficult computational problems usually already like come from quantum mechanics, especially quantum many physics, as you all know that the Hilbert space dimension usually grows exponentially in the number of system sizes. And of course, sometimes there are cases where you can get around it, but usually there's not. And these are the problems we would like to tackle. And one of them, and this might be also, of course, an interesting part for you, is the many-body localization. For those who might not be that much familiar with it, let me just give you a short intro to the introduction to many-body localization and also what aspect of it we consider. So maybe I like to picture it starting from Anderson localization, which is a single particle theory in a disordered medium. And once you introduce disorder into your medium, you observe a full breakdown of transport. And at least for the single particle theory, the mechanism of this breakdown is well understood. And you can picture it or approach it from various angles. For example, you can consider the spectrum of the localized in the localized phase compared to the non-localized phase, if you don't have any disorder, for example. Or you can also consider the eigenstates and how they give some notion of localization for the eigenstates as well. But yeah, the mechanism is well understood from a theoretical ground, and for example, these different aspects also sometimes imply each other. And maybe for some from some intuition, I also put a plot here where you have some, for example, local perturbation in form of this operator A. And then you can have a look at how information spreads in throughout the system upon this perturbation. And of course, if this fully delocalized, your information can spread ballistically with some velocity. Whereas this velocity really goes down to really zero if you have introduced any disorder into your system. And the similar aspect can be held for many-body localization, but now this is really now an interacting many-body system. And there you still have will have some phase transition between around some disorder parameter. Below you're delocalized again. This is you're delocalized, and if you increase your disorder above some threshold, you can observe a localized phase. But now it does not lead to a full breakdown because you still have interactions, even if your disorder is very large. So you have a very suppressed spreading. And in terms of this information spreading, this would correspond to like a logarithmic spreading in time. So basically an exponentially long time to traverse through the system. Moreover, this mechanism of the phase transition itself is not really understood from theoretical grounds compared to, for example, Anderson localization. And it's actually a very important question. I think there are some nice connections to classical statistical mechanics, and more also importantly to the term of thermalization. To study it numerically now, we consider the Heisenberg model, which is shown to exhibit many-body localization in this one dimension. So you have L many spin sites here, which are labeled through, and then the Hamiltonian of the Heisenberg model has two components. So the first one is a disorder term. You can just picture it as if you have spin sites now. These are really like local magnetic fields pointing in any direction at first now. And then, of course, you have interaction, which we assume to be nearest neighbor interaction. And they are also isotropical in the spin directions. So now we have disorder is also typically regarded something random, or at least quasi-random. And we take it as random, uniformly drawn from some interval. All these local magnetic fields, these local disorder terms, are drawn randomly from some interval, and this interval is parameterized by the disorder parameter h. Please keep this parameter in mind because it will pop up in all the later plots in our results. And moreover, this is assumed to have some really a critical value for this disorder parameter, which renders these two phases apart. This is a bit unclear whether this also holds in finite systems, but at least it's conjectured to have a distinct value then in the infinite size limit. And lastly, we also consider periodic boundary conditions on our spin chain such that the chain is actually a ring. Many-body localization has been really a test bed because of its maybe the difficulty as well as their relevance for lots of machine learning approaches. Not only machine learning, of course, there's a lot of numerics on it as well. But from our perspective, the machine learning perspective, there's a lot of works, especially using neural networks to try to do phase classification, even though you don't really 100% always know what phase you are in. And these methods use very different neural network architectures. I just listed a few here. And typically the goal is to infer an estimate of the critical disorder parameter such that you can draw like a phase diagram between these two phases and get really an estimate of this value. But, and this you can see from the input I listed here, this typically is very heavily pre-processed input. Like if you would have to feed in full eigenstates of the Hamiltonian, you don't gain any advantage in terms of computational efficiency, because eigenstates also, the size also grows in general exponentially with the size grows exponentially with the system size you consider. So that also in general sets a hard boundary on what system size you can approach. And yeah, to summarize this, usually you have computationally very costly pre-processing required. Okay, by the way, if there's any questions, please just interrupt me and we can just directly talk about this.
Well,
okay, now
since I know that is not the main point of your talk, but just can you go back? Can you say us something about what is, for example, to me, data augmentation? I mean, just to.
Yeah, sure. I left this a bit out because this is the only one which does not require pre-processed input, because it just takes directly disorder configurations, like these local disorder terms in there, and then they use it just
receive the HI, let's say.
Yeah, so exactly. Just receive the HIs and also as well the value of the disorder parameter, and then you can just sample new instances of your indicator value. So you have you generated a priori a data set, and then you train your neural network on it to gain more instances to enlarge your data set. This is called data augmentation. But this is just very pioneering work. It's also very hidden in the appendix, so it's not a major result of their paper in this regard. But I probably should mention it because this is like one of the only ones which don't have this highly pre-processed input. But yeah, good catch. Yeah, exactly. Because typically you have very computationally costly pre-processing. This sets a hard boundary on what you can do eventually in the system with respect to the system size you consider. And our approach is, can we skip this pre-processing in that sense? Like, of course, we have to have some data. And I said in the beginning, this should be treated as a given. So we somehow magically get access to it. But say we have it, can we directly, for example, input the whole Hamiltonian, and the Hamiltonian is just simply parameterized by the local disorder strength here, these HIs. And I will always sometimes also refer to it as a disorder vector, because you can basically picture it as a vector. And then find a mapping to some characteristics of the many-body localization of the phase, maybe of the phase transition mechanism. And these characteristics we are interested in are so-called indicators for MBL. And the indicators we consider, I will go through them a bit more in detail, but you can give them different types of what they consider. For example, you can consider how the eigenvectors have how they can be characterized, but also you can also consider how the energy, the spectrum of the Hamiltonian looks like in the two different phases. So we want to try to collect a few indicators from various which try to capture various different aspects of the transition. For example, they typically come from Anderson localization, also MBL, studying this numerically, and they try to capture different behaviors of the transition. Maybe let's go through them one by one. So the first one is the entanglement entropy. More precisely, we consider the half-chain entanglement entropy. For that, you take the system and split it into halves, A and B. And then you trace out one part, say the right half chain out, and calculate with that the reduced density matrix of the first half. And for this first half, you calculate the entanglement entropy given by this formula here. If you do that, let's imagine. Let's see what this should give us. If you're really very delocalized, have not much disorder in the system, the entanglement should be very large, right? Because because the interaction is the most prominent part then for your dynamics. And that means that your entanglement entropy should also be large, and you can somehow normalize this to a value close to 1. This would be the one phase, and the other phase, the many-body localized phase, you don't really have any more. So you still have nearest neighbor interactions, but the entanglement could not really be built up. So you have not much entanglement left. And if you picture this now in a plot, the x-axis will be the disorder parameter h. So this will be very often the case now in the following plots. And then you see on the left hand, and on the y-axis, the actual value of the normalized entanglement entropy. And you see that it actually goes down from value close to 1 down to value somewhere above 0. And you can also see that if you increase the system size, this descent, the steepness is increased a bit. And so you don't really go from 0 to 1, but from some values around it. But in the limit of infinite system size, it should really approach or it's assumed to approach some kind of step function around this critical disorder parameter. Right now you see some crossing, but this should not be taken too lightly as to say, okay, this is already my critical disorder parameter, which renders my two phases apart, but there's more theory involved if you want to use these indicator values here as already indication or to obtain an estimate for the critical disorder parameter. The next one is the dynamic spin fraction. And for that, we consider our spin subject to an initial spin wave present in our system. And the spin wave comes in form of this operator here. And then you consider eigenstates n of your Hamiltonian and calculate this formula on the left. And to give some intuition, it basically corresponds to the response of the system after some time to initial spin wave. And of course, if you are very localized, the spin wave will just basically somehow fade out. Your initial disposition will fade out, and after a while you won't find much anymore left. And due to this 1 minus, this should correspond to a value close to 1. So in the delocalized phase, you have a value close to 1. Whereas if you're localized, some of this information of the initial wave should persist throughout time. And that means that your value will go down to 0 due to the 1 minus.
Sorry, in the plot, you are averaging over n over the particular eigenstate, or?
Yeah, I average over particular eigenstates as well as repetitions of disorder vectors.
Oh,
so
okay.
Because the disorder is also averaged over a bit.
Mm-hmm.
Yeah, and then you see these kind of plots. Yes. But right now, this is just for demonstration. We'll show you. We go down one level before this averaging. But right now, it's just to give some intuition how these indicator values look like. Okay, the last one is the adjacent gap ratio, which tries to capture different aspects of the spectrum. So no eigenstates anymore, just the eigenvalues of the Hamiltonian. And you have two different. You see that they look quite different in the two phases. So in the delocalized phase, the energy spacings, so the differences between two subsequent energy levels, are described by the Gaussian orthogonal ensemble. Whereas if you're in the many body localized phase, basically you have uncorrelated energy levels, so that the spacings are described by a Poisson distribution. And numerically, you don't consider just the raw energy levels, but you take this quotient here from the minimum over the maximum, as it was demonstrated to be a bit more numerically stable over averaging or so. And then again, you find that it has two different limits. These are not 0 and 1, but somewhere in between, which you can calculate in these two limits. If you don't have any disorder, you can calculate a limit, and you can also calculate a limit what you would expect from the Poisson distribution for infinite disorder. So with that, are there any questions right now? Okay, then maybe let's come to our architecture and see how we can make use of these indicators, or how we can directly find a mapping between the disorder, really the local disorder values, and these indicator values. And for that, I will use recurrent neural networks. And I think for those who are not familiar with these types of different neural networks, let me give you a very short primer, like a 101 on this recurrent neural networks. And typically they come from the field of natural language processing. So, for example, machine translation, where you want to translate one language to another. And of course, in language, you know that sentences can be arbitrarily short or long. And so this is like a not a restriction, but an something which you have to make sure that your network can actually incorporate this degree of freedom that the input size can vary significantly. And for example, the recurrent neural networks are just designed in such a way that they can do this, that they leverage, they have this degree of freedom in varying input sizes. And how would you perform now? So what you would do is you basically feed in this the sentence here in German and would try to do like a word-by-word translation using this recurrent neural network. And how it actually what actually happens under the hood is the following: you would first iterate, so you would go iteratively over the input, so that the first word is just fed into just a basic neural network, just a very single layer of a neural network, and this gives you some output, like in this sense, just a word-by-word translation. But also the recurrent neural network retains a so-called hidden state, which is also fed into itself again. That's why I have drawn an arrow here on the left side. So there's some state which is looped back into itself, so some feedback loop in the recurrent neural network. And this hidden state is here propagated also as one output from the network to itself again, together with the next word. So the next word is also translated then word by word, but it's also conditioned on the first one, because information of the first word is somehow encoded in this hidden state. So this second word is of course translated, but conditioned on the first one already. And the same procedure holds for the third word, conditioned on the first two words. And so you come to the last one, and then you see that we have word by word translated this sentence from German to English. Of course, this is very oversimplified, right? In natural language processing, you have very more tricks, and also you would probably not do word by word translations, because usually sentences cannot be translated word by word, but you have more tricks. But this just gives you some intuition on how this recurrent neural network actually works like.
Sorry, if I understand correctly, the idea is that, of course, if you do a word-by-word translation, you will probably get a nonsense at the end.
Yeah.
So this, let's say, recurrent thing is, let's say, to adapt the translation word by word by the previous words.
Yeah, and to have this precondition, right? You have the end of the word or so is conditioned on the first ones as well.
Okay.
And that, of course, now you see that the sentence can be arbitrarily long as well, or short. It can be a 2-word sentence. It can be 100 words in a sentence, because the network here, so all these blue, this is really important. All these blue boxes here are the same network. That's really important. So you don't generate a new network for every sequence length, but it's the same network.
Mm-hmm. I see.
So the same network receives a hidden state and a new input, and can produce a new output and evolve the hidden state.
Is determined also. So my question was, if you have, let's say, 2 possible translations, you choose the one that make more sense with respect to the previous translation that you already did. Am I right? I mean,
Yeah, I mean, this is a bit too simple, right? Usually you don't do this. And also, so you can also modify your network that your output is not produced at every single instance. For example, you could also design the neural network such that the full hidden state is evolved, and then afterwards something appears. Then you can also do something like classification of sentences. For example, if it has a positive, if it's a positive sentence or a negative, so you can do multiple things with it, right? I just wanted to demonstrate a bit of the flexibility of the recurrent neural network, because we want to leverage this for our approach.
Okay. We have a question.
Sorry?
We have a question from Alexei.
Yes, please.
Yeah, just a simple question. So how does the recurrent network compare to the Markov chain? It sounds a bit like it, but I suspect there's some difference.
I think you can model a Markov chain by a recurrent neural network. By itself, neural networks are just function approximators, or I picture them as such. You can make these outputs probabilistic, and can give some information theory background on it, but you can also just do regression. And we will do
right. No, my question was actually a bit different. What I was trying to understand is that in the simplest Markov chain, basically your next state only depends on the previous one.
Yeah.
So here I was curious, when you walk over the sentence, so say when you start with this, and then the state you get for ease depends also on the previous word. But do you have like long-term memory, or is it you typically truncate? Say when you get to the sentence, do you only get input from A, or you also take into account like all the previous words in the sentence? Okay, so you have a long-term memory. Right?
Yeah, I mean, if there's really, so the network itself during training decides if there's a need for long-term training, right? This is because this is implicitly captured in the weights of the neural network during training. The network itself can say, okay, I need long-term memory effects or not. But we cannot tell. That's a problem. It's a bit of a black box. We cannot tell afterwards, really. But you can use it really as not only Markov, but like for a full, like this chain rule of probability kind of style, that you have really a condition on everything earlier.
Okay, thank you.
Yeah, no worries. Another question?
I think no.
Okay, then let's see how we translate this into our setting. And actually, it's quite straightforward, because we just exchange the words of our input into now this really local disorder strength, the HIs. And again, so this will be just we can picture this as a vector of length L. And the nice thing about this recurrent neural network now is that we don't care about the actual value of L. In particular, we can have instances where L is, say, 10, but you can also have 12, 14, 100 in principle. So in that sense, we can already try to using the recurrent neural network, we leverage the dependence on the spin chain size. And then how does it work in practice? Now we put in the first value and some initial hidden state, and don't produce any output right now, just propagate the hidden state one by one, step by step, until the whole sequence is exhausted. And then the last hidden state is just considered as the output of our recurrent neural network. And it gives us, and I will call it from now on, a set of features. And we will explain a bit more why to call it features at a later stage of my talk. For now, what you have to take home from this is that these features are now independent. So the features have a fixed size regardless of the actual value of L. So, for example, in our case, we have consider only two features, and this does not depend on the value of L. So the recurrent neural network really gives us a mapping from something which can be arbitrarily long or short to something fixed in size. And this is nice, because then you can use any classic standard neural network afterwards to map these features to the indicators right now. Why are they called features? Because at this stage, it's not, we have not really specified what our task is, right? We have not really specified what our output should be, and these features should be something which are more or less statements about the input, and they should not really be tied to the output per se. And we will test this, whether this is true in the later stage. For now, we map these features to the indicators, or to estimates of the indicator values, given for this really single instance of an Hamiltonian. And then to check whether we are correct or wrong, or how wrong we are, we can also directly build the Hamiltonian from this disorder vector, exactly diagonalize it to obtain the actual values of the indicators. And with this gives us also a training loop for the neural network architecture. Do you have questions to this?
Well, so here essentially you are saying you feed the neural network with a certain, let's say, H configuration. You let the neural network, let's say, predict or let's say train based on a label. So you're doing a supervised
Yeah, this is regression. This is really regression task. Yes, it's fully supervised. I mean, I have to, again, I have to have a training set, and this is this quantum data set, which I take as a given. Yes.
Okay, and then you, okay, maybe this is a question that should go at the end, but let's say, do you have any idea of what the neural network is learning? Because let's say from the physical viewpoint, let's say with our current knowledge is extremely hard, or let's say I think we have no idea how to detect if you are localized or not by simply the let's say the configuration of the disorder. I mean, this is something that
yes, I would maybe this is a good question for the end of the talk, because I will show I will also investigate a bit how these features look like and what we can actually do with this architecture and the following now.
Okay, thanks. Yeah,
but please remind me of this question afterwards. Yes. It's actually a very pressing one, because also neural networks have this this problem that they are basically black boxes, and sometimes it's hard to inspect what they actually do and what not.
Right.
Yeah, you're right with that. Yes, but maybe let's see what I did, and then you can ask further questions to that, and we can also discuss later on what can be done.
Yeah,
maybe.
thanks.
But thanks a lot for the question. So first, I start showing that we actually can learn this to the indicator approximation. For that, I set up two different system sizes. They're not very large, but in principle, you could, this is at least what I was capable of programming my own. I have some two system sizes, 10 and 12. So I already train my system on two different system sizes. And these are now, what I plotted here now are not only the mean values of the indicators, but also the standard deviation when you average over disorder parameter, different disorder configurations. So of course, also the exact diagonalization has some deviation around this, because there's randomness involved. And this is the orange plot, and interleaved with that is the output of our neural network in blue. And what you can see, at least qualitatively, is that the mean is nicely matched, most of the parts, and sometimes the standard deviation does not look too far off. This is now first only for the entanglement entropy. But I show you the other indicators in the next slide as well. But what is really cool now is that because we don't have any restriction on the system sizes per se, is that we can also query our model on a system size which is larger than 12. This is not, please keep in mind, this is not encountered during training. Of course, it knows how to deal with different system size, because I gave it 2 at least, but it has to infer from longer sequences now how this behavior should translate to a larger system size. And I benchmark this with actual results from exact diagonalization for L equals 14, and you see that this still seems to make sense, at least qualitatively, and I will show some quantitative results also as well. But you can see that for L equals 14, this kind of extrapolation seems to work, which is quite cool, because neural networks are not usually designed for extrapolation, but more for interpolation between data points. And to some degree, because we implicitly incorporated this spin chain dependence, it seems to work, at least if you're not too far off the system size of your training set. This not only holds for the entanglement entropy depicted in the upper left, but also for the other two indicators. At least for the adjacent gap ratio, at least the mean is nicely approximated. The standard deviation is a bit off though. But this is now all L equals 14, and this is a system size the neural network was not trained on. Please keep that in mind. We can make this more quantitative using the coefficient of determination. And the idea is that, of course, you will make some error, and this error you quantify by the mean squared error between the output of the network and the actual target values for the indicators. And then the coefficient tells you, okay, you are allowed to make more error where the target is actually has a quite large variance, because it can be noise, but it can also be randomness or so. And there you're allowed to make more mistakes, or larger mistakes, let's say. Then you do 1 minus, and then this is a so-called squared expression And this is really a value between 0 and 1 for linear regression. This is where it comes from. But you have to adapt it to nonlinear regression. It can happen that your error is larger than your variance, and then this value would be negative. And this is not really nice for a squared expression. But then you can normalize this again to the interval 0 and 1. And maybe what to take out from the next few plots I show you is that if you would have a perfect fit, this value would really be 1, because then your mean squared error is really 0 everywhere. Of course, this will not happen, even if you have like at least doing to numerical imperfections, but also, yeah, it's probably not likely that we have a perfect model. But we should aim for at least ideally to have some value around 1, and we would like to have at least a value of 0.5. This is like a baseline value, which says that if I only output the mean of my target, then I would attain this baseline value. Because then the mean squared error just turns into the variance basically again, and you obtain this baseline value. And everything below that is just bad. And what we see so these are the coefficient of determination calculated for various indicators, various system sizes, and independence of the disorder parameter again. And what you can see is for the most part, we are actually better than the baseline, especially around the assumed transition. So the transition is assumed around a disorder parameter of 6. And especially there, the neural network works actually best, which is quite nice because for the different phases, you have other methods which might be nice workingly. But for the transition is really the hard part, and there our network is actually quite good. And what we saw earlier, our qualitative look is actually verified here. We actually learn more than just the mean. It seems to be that at least also the standard deviations that we learned a bit. And this not only holds for the two different systems we trained on, but also for the extrapolation, which does not perform significantly worse for L = 14, the dashed line here.
Do you understand why the R ratios are generically worse? I mean, they are closer to the baseline.
Sorry, say it again.
I mean, if I understand correctly, the gap ratios are a bit worse, right? In the quality.
Yes.
Do we understand why the R ratios are a bit worse than the entropy or the spin fraction spin?
My understanding is that the quantity we're interested in, the adjacent gap ratio, might not be that smooth with respect to small changes in your input. Like if you, for example, turn just one local disorder parameter a bit, the adjacent gap ratio might not change smoothly anymore, I would assume, because you have this min-max terms there. This might be a case that, because neural networks basically assume a little bit of some kind of smoothness, right, to some degree. And this might, I think this is not the case compared to, for example, entanglement entropy. But I don't have a thorough answer for you here.
Mm-hmm.
But it just seems that the adjacent gap ratio is a bit more harder to approximate because it's probably related to the fact that it's not as smoothly varying with its input parameters with respect to them.
Okay, yes, thanks.
Yeah. Okay. Another result is considering the data set size used to efficiently train this, or to train this to some nice performance, because this is really important, right? Even if our architecture works perfectly, it does not give you a nice result if your training set required for that is very, very large, because remember, eventually this training set should come from a quantum experiment, and yeah, we don't want to repeat the quantum experiment millions of times, because this is also very costly and then also not feasible anymore. And what this part,
I'm not sure I get. No, okay, got it. Because you say you can generate, it's very cheap to generate the configuration of the HL. That is very cheap because
yes, you just randomly sample them. Yes,
right. But what is not cheap instead is to generate the SA that you need in order to train, right?
Yeah, the indicator values, the actual labels, if you want. These are not easy to generate. And if you would do a perform quantum experiment, which gives you somehow kind of these kinds of these indicators, it's really important that this number should not grow infinitely large.
Sure. Okay, got it. Yes.
And what I first verified, which is not shown here, of course, if you increase in general per se the training set, the performance gets better. But this is expected, because if you have more training set, more training data and have the same number of epochs for training, you have basically more update steps, and this is not really surprising. What I was interested in, if you take this product of the number of training points times the number of epochs a constant. Say, if I take half the data for training, I just train double as long, because then all the networks get the same number of update steps, but the update steps are just coming from a smaller subset of data. And what you can see here is now on the on the x-axis the number of training points, and on the y-axis is the average error we do. And what you see is that there's a plateau emerging. And I verified that actually this cannot really be decreased, like the training converged already. And you can nicely just ramp up the number of epochs and still get a very similar result, because you see that for the most part of this spectrum, and here this is logarithmically plotted, you get a very comparable error in the number of for the two different for the system size. So blue is 10, orange 12, and gray above extrapolation again. So it's a bit worse for L equals 14. And we verified that this is not a sign of like saying overfitting by seeing that the actual test data set, which was held out during not used for training, has actually a similar performance than the training data. This is not the case if we decrease the number of training points too much, of course, then yeah, we see that the discrepancy between the training set and the test set. This is because of overfitting. You basically try to just fit the data and not really the underlying structure below it. And you also see that the extrapolation capability just goes away. So the entrain now is not really just 3 data points, but 3 data points per disorder parameter we picked. So we have like 30 different values for the disorder parameter. And so this would correspond then to 90 data points here. So we have to multiply in that sense this with the number of 30 to get the number of data points we actually used for training. And this is really nice, because the number of 90 or 100 is not really large, right? And it's also in the order of the free parameters of the trainable parameters of our neural network. So that is encouraging for an actual experiment if you want to conduct such an experiment. And another result I have is comes from the field of transfer learning, and there I inspect the features. That's why I highlighted them here again in our workflow a bit more. The idea is that these features should be more statements about the input and not really too much tied to the output. And if you plot now the features, so if you train on the indicators and then you plot the features, they look like this. When you average again over disorder and plot them for different disorder parameters, they already look like a bit like an archetypical indicator. And the question is now, is that just because we have some indicators as output, and how robust are these indicators factually? And we test this by the transfer learning scheme, where you say you train these features, or you train your network on some indicators, but hold out one of the indicators. Then you fix the features and also fix the recurrent neural network, the parameters. Throw away the fully connected layer, because this maps the features to the indicators you just had, and then exchange the indicators to something new, which was not accounted during training. So example, later on, I just learned to train my network on the entanglement entropy and the adjacent gap ratio, and then exchange these indicators now to a dynamical spin fraction. then I just retrain the fully connected neural network, not the recurrent neural network anymore, and try to find a new mapping. And if these features are actually compatible or general enough, this should still work, right? And if it fails, it says that the features are actually more tied to the output than to the input. What I plot here in the next are 3 different schemes how to plot this. So the target is always the dynamic spin fraction. The blue line is what I showed you basically earlier. It's a multitask learning where you learn all 3 indicators at once, and I just plot this dynamic spin fraction. This is again here the coefficient of determination. Also for L=14, we have the extrapolation, as I showed you earlier. Then you, of course, have to compare it to training from scratch, where you just use your freshly initialized neural network and train just on the dynamic spin fraction. This performs equally well than the multitask learning. And then the last one in gray is the transfer learning script scheme, which I just explained to you. And you see that if you so you have to be a bit careful on how to adjust your architecture, but if you train properly, you see that you can reach a comparable performance, which is really interesting because it means that these features we extracted in the meantime seem to be like archetypical indicators. They can be mapped to indicators of different origin. Keep in mind, the dynamic spin fraction has shines some different light on the transition than compared, for example, to the adjacent gap ratio. But still, there seems to be some kind of compatibility between these various indicators, which is not understood right now for MBL. For Anderson localization, I think some of the indicators imply each other, but for MBL, this is not clear, and we give like now a positive indication that this seems to be the case.
Alexander, we have a question from Alexei.
Yeah, I have a naive question. Did you try a negative test to try and how should I say, to see if some indicator is not working well in this case?
Yeah, I tried the same transfer script with various targets, and it always seems to work. I mean, you have to be a bit careful. If you take, for example, too many features, there you run a bit into like try to fit a bit into what you want to achieve. So the number of features has to actually be quite small. Like this, I showed you 2 features, and that seems to work best. If you, for example, take more features, like more in between, this performs worse because then you try to fit into because the network tries to fit more into what is given to it, and then it uses a different combination of features in between. But for transfer learning, this really works if you have very small number of features. But
okay.
Yeah. So it seems in that regard a bit robust. Of course, I have not tried it with other indicators. I mean, there are still more to explore in principle. But for the 3 kinds we considered, and I mean, they are a bit different in what they try to capture of the transition, they seem to be compatible. But thanks for the question. Let me then come to the last part of my results, and this is obtaining a phase diagram of the transition. I mean, I already hinted towards this in the very beginning when I was also showing what others already did. And the idea is, again, the x-axis is the disorder parameter, and you of course have at one point a critical value for this, ideally, and then you can render these 2 phases apart. But there's also, you can also resolve this by the energy density. And the equation here is given on the right. You basically take in the energy you're currently considering, subtract the minimum energy, which is the ground state energy, and divide this by the range of the spectrum of the Hamiltonian, so that you get really a value between 0 and 1. And numerically, what was observed is that the actual critical disorder parameter depends on this energy density, and this is often referred to as the mobility edge of the transition, depicted here in red. And we would like to now so we would like to have to generate such a phase diagram. What would we have to do? First, we draw the axis, and then we say, okay, we pick some value for the disorder parameter and for the energy density. So a tuple, which then afterwards corresponds to 1 pixel in our phase diagram. Then we chose 100 instances of the disorder vector given the disorder parameter. And just to remind you, this is really drawn uniformly from this interval here. This is an L-dimensional vector drawn uniformly in its arguments, in its elements. What you then do is, using this H vector, you build up the Hamiltonian and diagonalize it and only keep a few eigenvectors or eigenlevels which are close to the chosen target energy epsilon. Then afterwards, you have 100 samples, you average the indicator value you obtained over these 100 samples. And you might already observe this, the very costly part is the diagonalization part, because again, your Hamiltonian grows exponentially with the system size, and this effectively sets a boundary on how large system sizes you can look at. And initially, I asked the question: can we skip this probe? Does this in a sense is pre-processing? Can we try to circumvent this? And the answer is yes, we can do so. If we can also generate with our neural network or our architecture such a phase diagram. And the nice thing is that the second step now is basically just a forward pass, and just putting the instances we sampled through the network and obtain already estimates for the indicators. And this can also be done depending on the value of epsilon. And this is not computationally efficient. This is computationally efficient compared to the diagonalization method. How do we incorporate the epsilon?
I didn't get this part. What do you mean by forward pass instances? And that?
You just plug in the values into your neural network and take out the indicator estimations.
But which values? The values of SA and so on? Eh?
Yeah, exactly. You pick just one indicator which for which you want to obtain the phase diagram, and then just simply.
But how do you get that values of SA? You need to do diagonalization, right?
No, of course, I need to do diagonalization for generating my training data. But afterwards, after I trained my neural network,
I see. Okay.
Of course, obtaining the data is not an easy task, but once you have it, you can get a computational efficient method which does not need to do diagonalization. In that sense, it's efficient.
Okay.
Provided you have, of course, training data. Yes.
Okay.
Yes. And how do we incorporate the energy density? Again, our plot from earlier, you feed in the disorder vector as input. The recurrent neural network evolves its hidden state, gives out these features, and then from the features are mapped to the indicator values. Because the features should be, how do we incorporate now the epsilon, the energy density? We put it like as an additional feature, if you like, because the features, as I said, are somewhat not tied to the output, but more to the input, and the input does not depend on the energy density. The energy density only comes in at a later stage. If you want to have the features and have these features independence, or the indicators later independence of the energy density. And you don't run into the problem of unbounded behavior, because energy density is just defined on the interval 0 to 1. So you don't have a problem that you have to turn up energy density up to arbitrary heights and have the network does not know how to deal with it. So that is quite nice. And if you do that, so the left part is basically using the training data or the test data of the data set to obtain here different. So I set up a grid for the disorder parameter as well as for the energy density, and you see that this is quite large pixels. This is like, I think, 30 times 20 pixels. This image. This is really generated from exactly diagonalizing the Hamiltonian. And then the right-hand side, I can just simply sample new instances of the disorder vector, make a forward pass through my network, and get a nicely resolved image. I can really turn up the resolution of the phase diagram. Please keep in mind, this is not mere interpolation. I don't take this image and just do interpolation between pixels. I go one level earlier onto the level of really characterizing single Hamiltonians and then averaging afterwards as a post-processing step. So this is not just mere interpolation between pixels here. So, so this is really nice. I try to do something more quantitative here, but right now I have to look into more details on my architecture to get something meaningful on a quantitative level. But at least for this qualitative data augmentation part, this is really nice. And it's simply a bit what we set out to do. With that, let me come to the conclusion. What I showed you is that we are able, given a data set, of course, and our architecture, we are able to characterize single instances or Hamiltonian instances for the study of many body localization. Due to the fact that we use recurrent neural networks, this method is in principle scalable in the chain size, in the system size, and only limited by the fact on what system sizes are incorporated into your training set. Moreover, we don't have any costly pre-processing, so we directly operate more or less the local disorder values. And to some degree, I showed you that extrapolation to higher system sizes becomes possible. Whether this really holds for if you go very far away from your system size, this is another question. I would suspect that at some point it will break down, but it's nice to know that it does not do something very weird once you go a little bit outside of your scope. So that's quite cool. And the next steps are then, of course, I mean, the setup cries for experimental really input, or at least a quantum simulation of a quantum experiment as input, and then see how our network also deals with noise in these experiments as well. And then from that, in principle, we can test our extrapolation further, because in principle, of course, performing the experiment is also not a trivial task, but in principle, you're not limited. You can go to higher system sizes in principle than you can do numerically. So in that sense, we can even test our extrapolation further. And altogether, in that sense, we envision a different type of quantum advantage where you can do something classically, which you can only do given a training set, because generating this training set is the hard part, right? Even if you have, but in principle, you could have a quantum experiment which generates your data, and then I can do a classical method using this neural network architecture to do something which I cannot do otherwise classically as efficient. With that, I thank you for your attention, and I'm happy to take questions.
Thank you, Alexander, for this wonderful presentation. Let us thank our speaker.
Thanks.
And we have time for questions. So perhaps let me start. Of course, you say you can extrapolate, and just for curiosity, probably you did try L18 and so on.
Yeah.
Is it so awful that you don't want to show it, or
yes,
is it still okay?
If you go until 20, it's too far off, because I only have 2 system sizes basically trained. And even if I train on 10, 12, and 14, 16 seems reasonable, 18, but I don't have data to quantify this. So I did not show it because, I mean, I can show you how it looks for L equals 100, but but the shape of the indicator also looks too far off. But my hope is that if you have a data set which consists of many more various system sizes, that the recurrent part knows how to stabilize this behavior, because the indicator values do not look too far, do look very similar to each other for various system sizes, right? I mean, they get more pronounced, yes, but in principle, the overall structure is the same. So, and I hope that this stabilizes the training. Mm-hmm. And eventually, I don't know, I think the neural network is not suitable, for example, to extrapolating for L equals to infinity or so, because you don't really know what happens there. And the network cannot also not know. You can try to infer from the data, but I think this is maybe not suitable for this. But once you have data, for example, for, I don't know, 30, 60 qubits or 40 qubits, you can do everything, for example, in between and a little bit far off or so. This is a bit more what I envision.
Is there any way to, I mean, without the corresponding training data, is it any way to, let's say, understand if a certain extrapolation is trustworthy or not? I mean, because this is also, this is always a little bit what neural network never tells, right? I mean, you never know if the result is trustworthy or not. So,
yeah, you don't get uncertainties on your prediction. That's true.
Right.
I mean, there are possible ways. There are proposed architectures that also incorporate like uncertainties into, or try to model uncertainties. But eventually, I guess that just then the network will just tell you, yeah, I'm just uncertain. And then you cannot. I mean, then you trust it that it's uncertain, but it does not tell you anything of use anymore. So I mean, this is just a bit. The extrapolation is a bit nicer feature, but it was not our main goal to extrapolate to any arbitrary heights, right? Because these methods are not they are not built for extrapolation. You have, and also on that note, there's not many machine learning models that can actually reliably extrapolate.
Right.
Also not, also apart also from neural networks. So this is a general question, I guess.
Maybe Alexei, you want to ask a question?
Yeah, well, it's actually a continuation. I was curious, did you try to play with some, well, it's still related to the extrapolation question. I'm just curious what happens if you take a model where you know the answer and you know, let's say for small system sizes, well, let's say that you need to go to large system sizes to actually see the correct behavior. So do you try playing with such models so to see whether you can train the networks to see the right behavior of even for small system sizes, where like the other, or say the conventional methods?
You mean models which are numerically attainable, or?
Yeah, I mean, I tried while I was like, while Thielen and Dario were asking, I was trying to think. So probably the thing that I could think of right now is the Anderson model on a random regular graph, where there was a speculation whether, so you have an Anderson transition there. So you have delocalized phase, localized one, and there was a long speculation whether there's an intermediate non-ergodic phase. I think it has now been settled in favor of there being no such phase, but this model is known to have, and if you try to do the finite size scaling, I think the claim is that the finite size corrections there are huge, and even though it's a single particle problem, you cannot really reach the sizes where these corrections are small. So, so yeah, I mean, for the moment, I cannot suggest any other models, but I'm curious to know whether if you consider this option, or if you think that makes sense to look at.
That makes sense to look at. I have not considered it yet. I actually have not really considered any other problems because many-body localization took a lot of my time already. But it would be nice to actually see how this model, or what you can do on other parts, especially also where you can approach things numerically easier because it has a nicer structure, so you can easily simulate it or so, because then you can already test this extrapolation a bit more. Yes, I agree. This is definitely
well. Then probably I would look at this random regular graph Anderson model, the other model, but I'm less sure. I think the random field Ising model, which in 2 dimensions, which is known to that the ferromagnetic phase there is unstable for arbitrarily weak fields. So no matter how weak a magnetic field, a random magnetic field you add, it immediately destroys the ferromagnetic phase.
Oh, thanks for the suggestions. Yeah, I will have a look at them.
Alexei, am I right? So the interacting particles could be a suitable model, because there you see the wrong, let's say, scaling when the system size is too small, and to see the right scaling, you need to go very large. So maybe there you could.
I mean, it fits the formal criteria, but somehow my intuition is saying no, that's not the right one. But I might be wrong. Maybe that's also worth thinking about.
Mm-hmm.
So,
And also, yeah, let me go back to the question that I asked during the talk. So do you have any way to understand what the neural network is? Because as I said, I mean, theoretically, I'm quite surprised that by just, no, of course, I'm not quite surprised because actually the model is specified by the values of the magnetic field. So at the end, once you give the magnetic field, you need to be able to compute everything.
Yeah.
However, I never heard about the possibility of learning, let's say, algorithmically, the values of the, let's say, the entanglement entropy or so on, directly from the values of the magnetic field. So is there any way to understand? Because that will be also, I mean, let's say neural networks will be fascinating in two cases, either if you can extrapolate, or you can use them as tools to, let's say, provide something, some physical principle maybe that we don't know yet. So the idea is that the neural network learns something that we don't know yet, and the idea is that then we learn what the neural network has learned, and maybe we learn something new also for us. Is there a way to detect what the neural network learned?
I mean, usually you can only relate input to output relations, such as, I mean, I showed you the features in a sense.
Yeah.
That gives you an understanding because they already look like a bit like an indicator already. And you have these different spacings between different chain sizes. So that gives you some look under the hood. But apart from that, I would like, so in the future, I would also like to experiment with like detuning a single size or so. Pick a single spin and turn up or turn down the local magnetization strength. Because then you can see how smoothly, if the values actually change smoothly or not. Because what is typically believed for neural networks is that they find some kind of high dimensional manifold, and that's like something which is neighboring in the input space is also neighboring on this manifold.
Mm-hmm.
And I guess that is also still why it works, but like getting into look into this manifold is, I guess, hard.
Mm-hmm.
But this is a general question again for neural networks.
Yeah.
I mean, there are some heuristical methods, I think, to picture or to go into this a bit.
I'm really asking about for something that for me is a slogan, but I heard about this dreaming. I mean, I heard some like dreaming algorithm or something like that.
Yeah, the dreaming would also be interesting. Then you can, but this is more for classification tasks where you already have a label, and then say what makes or what input really makes this label, or what is really what input is typical for this label.
I see. Okay.
But this is more for classification tasks. And I would like to do a classification. Originally, when I started my master's thesis on this topic, I was planning to do some more classification tasks using neural networks. But then I mean, there's lots of works on this classification, and all of them are really not. I mean, the transition is hard to capture. That's why it's attracting lot of attention. But it's also hard for neural networks to really find something. But it would be nice. I mean, I already tried to do something like doing regression, like this regression type, and also classification type doing the same forward pass, because then the network has to do both things at once and maybe intertwine it a bit. But I'm experimenting with this, and I have not yet results for this. But yes, you are right. I mean, this is like eventually what you want to draw out of this model as a physicist. Yes.
Yeah. Alexei?
Well, yeah, it's again a follow-up to the previous question. Because essentially my expectation would be if it's also related probably to extrapolation, that if this whole thing works, so if you manage to show that you can do extrapolation and understand what the network is actually learning, then a natural question then would be, so what is then the best indicator in this case? Because I think so far people use the various indicators, well, simply because that was their intuition. But my understanding is that the power of the neural networks is that actually it's able to detect things that humans, for one reason or the other, are not able to see, either due to lack of imagination or due to whatever. So did you try to see what if you can extract some, I mean, did you try to construct a better indicators based on the results you get?
I mean, in a sense, you can picture the features as an indicator, but the problem is, maybe can go back to this slide. The problem is that we have it there. That you see that the level crossing is at different positions for the different features, and this is not fixed for when you retrain your neural network. So it cannot directly tell from this feature where, for example, the disorder parameters. It gives you like, it can shift around a little bit, and I mean, it does not make it. The problem is the network is a bit. It has these translation invariants that you don't know where to exactly pinpoint the value here, right? So I think trying to extract really a new indicator is a bit problematic. And also, if you want to, I mean, this is what you're hinting to is a bit also, it's a double-edged sword, because of course maybe there is some hidden structure which your network knows, but then you also don't know if it's really a hidden structure or it's just a pattern which is just available in the data because you have a finite set of data. Maybe the network finds some pattern in the data which is not there for the whole data. Or if like there might be a pattern which is visible in one data set and not visible in the other. And networks typically tend to find patterns even if there are none in the data.
Yeah, well, I mean, this last thing I think, well, we're a bit on the safer ground, because I think, you know, it's always easier to explain why a certain indicator is good when you already know what this indicator is. So yeah, I wouldn't worry that much about it. Okay, thanks.
Yeah.
Do we have any further questions from the audience? Seems not. So in that case, let us thank Alexander again.
Thanks a lot.
And